Hi, in this lecture on demand, I will be discussing Lewis dot structures and how they vary slightly in the way that organic chemists think about them from what we learned in general chemistry. Just to review, in Gen Chem, we drew a whole molecule and then distributed the electrons. In organic chemistry, we're going to look at specific atoms and how they exist in terms of their Lewis dot structure, because organic chemistry pretty much deals only with carbon, nitrogen, oxygen, and the halogens, fluorine, chlorine, bromine, and iodine, plus hydrogen, of course. So let's think about carbon first. Carbon is neutral and stable and it has 4 bonds, as you know. So here's a carbon with 4 bonds. These are 4 single bonds, but you could also have carbons with a double bond and 2 single bonds, or a triple bond and 1 single bond, or 2 double bonds. And those all are stable and neutral because they have 4 bonds. Now, why is carbon stable and it has 4 bonds? Specifically because, first of all, the octet rule is obeyed. Each carbon has a total of 8 electrons around it. And secondly, carbon has a valence of 4 due to its position on the periodic table. And remember how we count valence electrons, 1 from each bond. So 1, 2, 3, 4. All the rest of these have 4 valence electrons. So it follows the octet rule and it has the proper valence when carbon has 4 bonds. But carbon may also have a charge. So in some cases, we'll see that it will have a positive charge, and that can happen only when there are 3 bonds to carbon and no lone pairs. Specifically, then it has a valence of 3 instead of 4, so it has to have a +1 formal charge, thus the positive charge. I've drawn a circle around the positive charge here to emphasize it. Now, why is carbon positive when it has 3 bonds and no dots? Again, because the valence is 3 instead of 4. Carbon's supposed to be 4, so it's missing 1 electron, so it has a positive charge. These kinds of molecules are called carbocations, and it turns out they're very unstable because they are missing an octet. The octet rule is very important in organic chemistry, and since these kinds of carbocations don't have an octet, they tend to be very unstable. Not the kind of molecule you can put in a bottle, but only seen for vanishingly short periods of time. On the other hand, negative carbons do have an octet. 1 lone pair and 3 bonded pairs for a total of 5 valence electrons, and therefore the carbon is negative because it has 1 extra electron. These kinds of molecules are called carbanions. Carbanions can be stable in some cases. In fact, you can probably think of a case from general chemistry where carbon had a negative charge in one of the polyatomic ions that we learned about. I'll let you review that, go back and think about it, and see if you can come up with a case where a carbon with a negative charge is actually stable. But most of the time, they aren't. So to review, when carbon has 4 bonds and no lone pairs, it is stable. When it has 3 bonds and a lone pair, it has a negative charge. These may be stable, but are usually not. And when it has 3 bonds and no extra electrons, it will end up having a positive charge, and these are never stable due to the octet rule. Now let's consider nitrogen. Notice that when it's stable and neutral, it has 3 bonds and 1 lone pair. And there are other ways in which that can happen. 3 single bonds and 1 lone pair, a double bond and a single bond, and 1 lone pair, or a triple bond and 1 lone pair. But in each case, it's really 3 bonds and a lone pair, and that means that it's going to be a stable situation. That's the typical nitrogen situation. Why? Because it follows the octet rule. Again, total of 8 electrons, 2, 4, 6, 8, and 5 valence electrons, 1, 2, 3, 4, 5. Can you think of an example from general chemistry that we learned about where nitrogen has 3 bonds and a lone pair and is a neutral molecule? Now, like carbon, nitrogen can be charged. In this case, it has 4 single bonds and a positive charge. Anytime nitrogen has 4 bonds and no lone pairs, it will have a positive charge. Again, can you think of an example like that from general chemistry? Go back and review your polyatomic ions. These ions tend to be quite stable. On the other hand, nitrogen with 2 single bonds and 2 lone pairs will be negative. These ions are also stable, although we don't see them very commonly. And again, it's negative because of the 1, 2, 3, 4, 5, 6 valence electrons. It's supposed to only have 5, so it has 1 extra one, so it's negative. Let's think about oxygen. Oxygen typically will have 2 bonds and 2 lone pairs, either 2 single bonds or a double bond and 2 lone pairs. Why is this a stable situation for oxygen? again, because the octet rule is satisfied, and so is the valence. Oxygen is supposed to be 6, and it has 1, 2, 3, 4, 5, 6, and therefore that's a stable situation. Like carbon and nitrogen, oxygen can be charged. In this case, it has 3 bonds and 1 lone pair, therefore a valence of 5 instead of 6, therefore a +1 charge. You probably can think of a very famous example in which oxygen has 3 bonds and 1 lone pair and a positive charge. These ions are in fact stable, at least in solution, although we generally don't see them unless they're in water solution, but they can be considered to be stable. Why? Because they follow the octet rule. That's the basic reason. On the other hand, oxygen can have a negative charge. In this case, it has 3 lone pairs and 1 bond. Again, the octet rule is satisfied, but it has an extra valence electron, 1, 2, 3, 4, 5, 6, 7, and therefore a negative charge. Again, this is a pretty stable situation, and hopefully you can think of several cases in which we've learned ions that have negative oxygen with 3 lone pairs and a single. Now let's think about the halogens. The halogens, fluorine, chlorine, bromine, and iodine, are generally considered together as one group and symbolized as X. So if you see a capital X in a structure, it means chlorine, fluorine, bromine, or iodine. The halogens are stable and neutral when they have 3 lone pairs and 1 bond. Obviously, it has to be a single bond if there's only one. And that's because, again, it follows the octet rule, 2, 4, 6, 8, but has a total of 1, 2, 3, 4, 5, 6, 7 valence electrons, and that's what the halogens are supposed to be since they're in column number 7, and therefore it follows the octet rule and it has the correct valence. So this is the typical situation with halogen. It will just have one bond to something. But like carbon, nitrogen, and oxygen, halogens can be charged. Notice that if it has 2 single bonds and 2 lone pairs, it will have to have a positive charge because it only has 6 valence electrons instead of 7. It still follows the octet rule, however. These ions typically are not very stable, and we won't see them very often, but they can be because they follow the octet rule. On the other hand, halogens with 4 lone pairs and no bonds will always have a negative charge, and these follow the octet rule, but they have 1 extra electron, so therefore they are negative. These ions tend to be very stable, and in fact so stable that they are commonly found in the environment, even in our food. You probably ate some for breakfast this morning in the form of chloride. Sodium chloride is salt. Chloride is chlorine with 4 lone pairs and a negative charge. So let's review. What I've done here is I've arranged the various neutral molecules and ions that we've talked about in this into columns. Notice that this one is off to the side. That's for a special reason. Why is this different from all the rest of them? Because it does not follow the octet rule. Notice it only has, like I said, 6 total electrons instead of 8. This is called a carbocation. These tend to be very unstable, and they are not like the rest of these. All the rest of these, in fact, follow the octet rule. Notice every single one of them has a total of 8 electrons around them. The difference is their valences and therefore their charge. Carbon, when it has 4 bonds, is the correct valence, so it's neutral. Nitrogen, when it has 4 bonds, has 1 less electron than it should have, nitrogen being a valence of 5, therefore it's positive. Carbon, when it has 3 bonds and a lone pair, is negative. Nitrogen, when it has 3 bonds and a lone pair, is neutral because it has the correct valence. Oxygen, when it has 3 bonds and a lone pair, is positive because its valence is 6 and it only has 5. Similarly, nitrogen with 2 bonds and 2 lone pairs is negative. Oxygen with 2 bonds and 2 lone pairs is neutral. Halogen with 2 bonds and 2 lone pairs is positive. Oxygen with 3 lone pairs and a single bond is negative. Halogen with 3 lone pairs and a single bond is neutral. And halogens with 4 lone pairs are negative. On the other hand, we can go down the columns. Notice that carbon, nitrogen, oxygen, halogens each can carry a -1 charge. But for carbon, it has to be 3 bonds on a lone pair. For nitrogen, 2 bonds and 2 lone pairs. For an oxygen, 1 bond and 3 lone pairs. And for halogen, 4 lone pairs. Similarly, the neutral atom, carbon has 4 bonds, nitrogen has 3, oxygen has 2, halogens have 1. For the positive ions, nitrogen has 4, oxygen has 3, halogens have 2. And then you might wonder, is there something could fit in this space in which carbon would have 2, 3, 4, 5 bonds and a negative charge? And I'll let you think about why that's not possible. We can talk about it in class. But carbon can be positive, however, it has to not follow the octet rule, and that's a special case. So, do you need to memorize these? I would say yes and no. Like most things in chemistry, there is some memorization involved, but it makes it a lot easier to memorize if you understand the concept. So you can simply memorize and recognize when you see one of these things that it is correct. When you see something that's wrong with one of these, it's probably not correct. And we'll get to some examples like that in a minute. But if you understand the theory behind why these are correct, then you don't really have to memorize them. Now, here are some structures for you to look at, and I'm not going to spend a lot of time with these. I'll let you spend time looking at them at your leisure. But some of these are correct, and some of them are not correct. In a couple cases, the octet rule is broken. In a couple cases, the formal charge is incorrect or missing. And in some cases, they are correct. So I'll let you look at these, and we can talk about them in class. But I would ask you to further study by drawing structures on your own. Just go crazy. Put in structures with carbons, nitrogens, oxygens, halogens, hydrogens, single, double, triple bonds, lone pairs, but make sure that the structures that you draw are correct. You can certainly draw incorrect structures, but make sure you're drawing the structures correctly so that, for example, carbon has 4 bonds if it's neutral, nitrogen has 3 bonds if it's neutral, or 4 bonds if it's positive, and so on. Thank you for your attention.